So the term CPU stands for Central Processing Unit. So the idea here is that in a computer, you have two fundamental components. If you remember from the first lesson, a computer is made up of two fundamental components, which is the hardware and the software. So the hardware components are made up of your input devices, your output devices, your storage, communication, and your processors, whereas your software section or your software component is made up of the operating system and system software. So it's important to understand the position and the place of the CPU. The term central processing unit, this word central, indicates that inside a computer, there's actually more than one processor. So what is a processor? A processor is basically a circuit element. It's made up of logic gates. The logic gates we covered last week. It's made up of logic gates, and it transforms itself into the logic of a particular program in order to transform input into output. So we want to go ahead and start on our whiteboard here, or rather blackboard. We want to go ahead and start defining a couple of things, very important things for us to remember. First and foremost, the fact that the computer itself is made up of these two subcomponents. So I mentioned the hardware, which is what computer architecture is concerned with. So you have your input hardware. Those are all the hardware that can accept input signals. So if you remember from data representation, we said anything you want to communicate to the computer, any data you want to pass in, has to be passed in via some type of input device. So your trackpad, you use it for left clicking and right clicking. Your keyboard, you use it for typing in text. So your microphone for audio, all of these are input devices. So input devices are essentially electrical components that collect information in the real world and translate or transfer that information into the computer. Then you have your output devices. Those are the devices that take the computer's data and present it to the real world, either to a human being or to another system. So your speakers, your screen, and so on. And then, like we mentioned, your processors. Your processor is what does the transformation. So typically, the architecture of a computer can be represented as input, then process, and then output. So we did mention earlier on that the input is the information about the world for enough for computing needs. Information about the world, enough for computing needs. Now, if you understand this at a fundamental level, computers will make a little bit more sense. Think of a computer like a calculator. What does a calculator do? It crunches numbers. So if you have a simple calculator, you would have, addition, subtraction, multiplication, and division. So if you have a calculator, you need to input your equation. Then the calculator needs to process and generate a result, which the calculator's display will then churn out to you. So let's say I had an equation that I wanted to calculate. The input device on the calculator will be what? The number pad. So that number pad allows me to send a signal, which is what we're representing here. It sends a signal that carries information about the real world enough for our computing needs. In other words, it describes our problem. That is an input signal. So an input signal can be of two types. It can represent an instruction given or data fed into the computer. So in the case of a calculator, let's say in a calculator, I inserted the equation 3 plus 2. And I wanted that calculated. What the computer will do is it will recognize 3 and 2 as numerical data, and it will then recognize the addition as an operational code. In other words, the plus is the instruction on what to do. The 3 and the 2, we can label those 3 and 2 A and B. So the A and B are the data elements on which the operation is going to be performed on. Now, this is a very simple mathematical example, but everything else your computer does is exactly the same. If you want to view an image, you double click on the image file. The image file is data. The operation is convert this data file into an image on a screen. So your processor is involved. The input will be the instruction that you double click to open the image. Then the processor takes in the data that makes up the image file, and then translates it to something that is displayed on your screen. So what's displayed on your screen is the output. So the output is the result of computation. So result of computation. I hope that's clear to everyone. So the processing, we said, is the transformation of input into output. So it's enough for you to understand the processing as transformation. So with this basic definition, you figure out that the computer is really just a glorified calculator. The power of the computer comes from the ability it has to run different software. So by installing applications, you can get the computer to process data differently. Just like a calculator, you can input data and you can say, do addition, do subtraction, do multiplication. The computer, you can say, render an image, transmit a message when I'm using the web browser, transmit a message to the internet and receive a response and generate the data for me in a form that is readable, viewable, and whatnot. You can say play a computer game. You can say play a movie file, which is basically translate this data file into image and sound for me. So everything you tell your computer to do is an instruction that is associated with data that involves some sort of transformation. So that is what the CPU does. It transforms input into output. And the input is two things, data and instructions. And the output is the result of that computation. So the output can be anything depending on what operation you perform. Now, if you've understood this, you've understood the fundamentals of today's lesson. The only thing that's left is to look at the nitty-gritty and to figure things out. So when we talk of the processor, remember, we call it the CPU. Now, in some textbooks, it will be said that the CPU is the brain of the computer. That is not a fair description. The reason why it's not a fair description is the brain is 1,000 million times probably more complicated than a processor. The processor is not a brain. It's literally an electrical component that accepts input and processes that output, processes that input via a set of instructions called software and generates output. But it gets a little confusing. In a typical computer, when a computer is turned on, what exactly is happening? What is running in the background? What is running in the foreground? How does processing actually happen? This is what we're going to attempt to understand. Before we do that, though, we need to understand that the term central processing unit refers to the main processor in a computer, which implies we have other processors inside. Your GPU, your graphics processing unit, is a processor. Your sound card is a processor. Your network interface card, that's the part that contains your Wi-Fi, your Bluetooth, and your Ethernet, is also a processor. So the term central processor indicates that this particular CPU, this particular processor, controls everything else. That's why we call it the central. It's at the center. That's why they call it the brain. It's in the middle of everything. In other words, it controls and coordinates everything. How are you supposed to conceptualize that? I want you to imagine here in my hand, I have this remote control. I want you to imagine that everything in this classroom is connected to this remote control. So if I wanted to control the doors, the lights, the air conditioning, the projector, anything, I go through this remote control. It's the central operating unit, if you like. It's connected to everything else. And through it, I can control everything else. This is how the CPU is to your computer. It's literally physically connected to every single thing. It's connected physically to every single item. And it controls and coordinates every single item in the same way when we looked at that toy car with the 4 motors. So the toy car with the 4 motors was connected to a motherboard and connected to a battery. And by allowing electricity to flow to certain components, we got the toy car, to behave in a particular way. So in the same way, the processor is connected to everything. And if we turn on certain switches inside it and turn off certain switches, it will implement the logic of a program such that input can come and be transmitted to other components and processing can happen and results can then be generated. So in today's lesson, we're going to see what components make up the CPU and how it operates overall. So the final components are, of course, the storage and the communication components. On the other side here, we have the software components, which include the operating system and the application software. Right. So now we can draw a proper diagram that shows us the fundamental components of our computer. So I'll go ahead here and insert a couple of cubes. So first of all, I'm going to start by drawing this rectangle, and this rectangle is going to represent my hard drive. So this hard drive is my storage. That's where all my data and instructions reside. I will again then insert another rectangle that is going to represent my RAM. So this is my random access memory. It's also known as my my primary memory, or just simply memory. That's another word for it. Then I will insert another rectangle down here to represent all my input-output devices, so my I/O devices. Then I will go ahead and insert another component called the cache controller. So C.C stands for cache controller. What is the cache? We will explain it in a moment. And then we can start building the CPU. So the first component of the CPU is called the CU. That stands for control unit. The next is the arithmetic and logic unit. So we call it the ALU. And then lastly, we have another component called the registers. So the registers are like small storage locations that store the data that the CPU is currently working on. So it's plural, registers. So I'm going to put the plural S in red letters just to remind you. So all in all, together, these components make up the CPU. So everything here is actually part of the CPU chip. So this is the CPU. Now, in between all of these components, I'm going to draw arrows. And these arrows are going to represent the connection between each of the components. So these arrows represent what we call buses. In a computer, a bus is simply a cable that connects two or more devices together. So it's just a device that connects two or more components together. It's an electrical wire. So if you strip down a computer, you unscrew it, you take out all the plastic bits, and you expose it, you're going to see all of these buses. And notice that the arrows I'm drawing are bidirectional. Because they're bidirectional, it means data can travel to and fro from each of these components. So this noun becomes the map that we're going to use to understand the CPU and the memory, the relationship between these two important components. The CPU is the device that transforms input into output. The memory, I'm going to write this down here, which is called the RAM, is the part of the, or is the component that stores the data and the instructions that are currently being worked on. In order to explain this, I'm going to give you an analogy. I want you to imagine my desk, this desk that I'm sitting on right now. So for those of you at home, let me use an image of a desk. So I'll type office desk so that we can just have an image, and I'll go into images. So let me use this image. So here I have an office desk. So this office desk is my workstation. So I want you to imagine right now, when I get to work, let's say this is my office. I have a bag, a school bag. Inside this school bag, I have my computer, a couple of documents, some writing tools, and so on and so forth. So in other words, all the tools and all the data that I need to do my work are stored inside this bag. So this bag is like my storage device. So in this architecture, the storage, the hard drive, contains all of the data and all of the tools, which is software that I'm going to be using on my computer. The bag contains all of my stuff. Now, if I want to start working, I need to open up my bag and take out whatever it is. If it's my computer, I take it out and I put it on my desktop. If I have a document that I want to read or I want to reference, I take out the document and I put it on the table. Now, as I'm putting things on this table, they're going to be occupying space. As you can see here, the computer I placed on the desk occupies some space. So the space on my desk, which is my work area, is what the RAM is. So the RAM is the work area. Let's go ahead and label it. So this RAM here is the work area. So any data or any tool I put onto the table occupies space. So there's a finite amount of space on my table for me to work with. And that is how your RAM operates. So this means, let me open up my activity monitor. If you're on a Windows system, you can right click on your taskbar to open up your task manager. So on my activity monitor on my Mac, I have here a list of all the programs that are currently running. So these are the tools, the files, and the data that are actually operating. And you can see there are lots of them. And here you can see how much memory each one is consuming. So if I order them according to their memory consumption, and I go to the top of the list, you can see here, Microsoft Teams is amongst the top programs that is actually consuming memory space. It's occupying about 700 meg. So it means on this theoretical table that I have, that the Microsoft Teams application, if my table is 8 gig, the Microsoft Teams has taken 700 meg already. So the more things I open, the fuller my memory becomes. And at a certain point in time, my memory can become overfull. And at that time, when my memory becomes overfull, my computer might start to slow down and show me signs of hiccup and whatnot. There are techniques that the operating system uses to deal with this, but ultimately that is what the memory is. So I want you to imagine now on my hard drive, I have all the tools I need. So let's say I wanted to perform an action or perform an operation. Let's say I wanted to listen to some music on my computer. On my hard drive here, I will have two particular type of files that are of interest. One is going to be a .exe file, which might be something like VLC player. Everybody's familiar with VLC player, I hope. It's this media player thing. And then here, let's say I have an MP3 file, which contains the music that I have. So this will be a .mp3 file. So I'm going to label this MJ for Michael Jackson. So let's say I want to listen to a Michael Jackson song. I double click on the file, what happens? How does the processor operate? The first thing that happens is this. These two files represent the data and the instruction by which the data is going to be transformed. 3 plus 2. The plus is the operation, the 3 and the 2 is the data. Here, the Michael Jackson file is the data, and the VLC contains the instructions of how to transform that data file into sound, and if it's a movie, into video and sound. So the first thing that will happen is we will copy the data into memory. So it means if this data file is 3 meg, we will occupy 3 meg of memory just to open that file. So far, so good? So remember, listen to the word I said. I didn't say we open the file and put it on memory. I said we copy the file. The original still remains in memory. So while it's on memory, the original is still in the hard drive. Unless I make changes and I say save, then the copy that is in memory will be used to overwrite that is in the hard drive. So it's a copy. Once the copy has been opened, the CPU can then begin work. So what does the CPU do? The CPU performs 4 operations continuously in a cycle. These operations are, first of all, it fetches the data. Second, it decodes the data. Third, it executes the instructions. And 4, it stores the result. Fetch, decode, execute, store. If you're sleeping as a computing student and they wake you up from sleep, you should be able to remember this. What does the CPU do? Fetch, decode, execute, store. So when we say fetch, what do we mean? You see here right now on our system, we have a situation where we're trying to open up an MP3 file. We've double clicked on it. The instruction that the computer has run now is to make a copy of the file and the data into the RAM. So right now they're occupying some space inside memory. So when we're ready to begin operating, what needs to now happen is bits and pieces of this instruction and this data will be picked up and we will begin operating on it. Think of it this way. As a human being, let us say you have a document that you want to read. So you fetch the document from your hard drive, from your bag. So you open it, it's on your memory. You want to start reading. When you open up the first page, you use your eyes to read. And how do you actually read? Your eyes recognize every single character, and you start constructing words, and you join the words to form sentences. And only the time when you reach the end of a sentence will that sentence make sense. So in other words, you'll be loading till you reach a full stop. So you've read one full sentence, then you translate it in your brain, and then it tells you what it means. Does that make sense? So in the same way, if you're writing computer programs using Java or whatever programming language, when the files are loaded onto RAM and the CPU is about to execute them, you don't take the entire program and translate. You take line by line. So when we say fetch, it's just like what you're doing. When you're reading a book, you don't read the entire page or the entire book at once. You read line by line, paragraph by paragraph, page by page, section by section, chapter by chapter. Same thing the computer does. So this fetch, decode, execute, store, fetch, decode, execute, store, what we're fetching is single lines of single instructions. I hope that's clear. So when you fetch that code, where does it go? You fetch it from the RAM and it goes into the registers. So what is the register? You can think of the register as the storage for the CPU. I repeat, you can think of the registers as the storage for the CPU. What do I mean? Let's say I tell you a story about Adam. I say Adam went to the kitchen and fetched a cup of water. Where was the water stored that Adam fetched? Adam went to the kitchen and fetched a cup of water. Where is the water stored that Adam fetched? Listen to the sentence again. Adam went to the kitchen and fetched a cup of water. Where is the water that Adam fetched stored? God Almighty. You guys speak English, right? I repeat, Adam went to the kitchen and fetched a cup of water. Thank you. The water is in the cup. So the cup is Adam's register. You get it? The kitchen is like the RAM where everything is. So he went into the RAM to fetch a cup of water. So when he fetched, what I'm trying to get you to understand is if the CPU is going to fetch something, it needs some place to keep it. So that someplace it keeps what it fetches is the register. So I'll give you a quick example on the side note. So let's say my computer wanted to perform this 3 + 2 operation. The 3 is data, the 2 is data, and the addition is the operation. So what needs to happen is this. The 3 needs to be stored in a register. The other 2 also needs to be stored in a register. Does that make sense? So now you have these 2 data pieces stored in different registers inside the CPU. So now the instruction is add the first to the second. So because you fetched A and you fetched B, now you can add A to B and put it in another variable maybe called C. Very simple. So when you fetch, you store it inside the register. I hope that's clear. We'll come back to registers later. So the fetching is handled by the CU. So the CU here stands for control unit. The decoding, that is figuring out what does this instruction mean, is also performed by the CU. So the CU stands for control unit. And the job of the control unit is, 1, the movement of data in and out of the CPU. Now, in English, in all languages, there's something we call ambiguity. Ambiguity means a statement that is not absolutely clear. For example, if I say Adam went to the bank, Do I mean Adam went to the financial bank, or Adam went to a beach? You know, the beach is also called a bank. So the word bank is ambiguous because it can mean financial institution, or it can mean a coastline, a beach. So in the same way, when we say movement of data, I need you to understand that this data here is a general term that can be used to describe instructions and data. So this data here can represent an instruction, and it can also represent regular data. So when we say data, generally we mean data or instructions. So that's what the control unit is responsible for. The second thing the control unit is responsible for is decoding information. So decoding means figuring out what the instruction actually wants. So you say do 3 plus 2. The plus is the instruction, the 3 and the 2 are the data pieces. So if a computer CPU is going to execute 3 plus 2, the first thing we need to do is fetch the instruction. What is the instruction? 3 plus 2. In reality, the instruction won't be 3 plus 2. It will actually be something that looks like this. C is equals to A plus B, where A might store 3 and B might store 2. I hope that makes sense. So C equals to A plus B is a typical instruction. C is the address where we store the result. A and B is the address where the data that we're going to be performing an operation is on. And the plus is the actual operation code. I want to pause here and let that digest a bit. This is a very important key. Every instruction has a format. When the CPU fetches the instruction, the format of the instruction, remember, is a sequence of zeros and ones. And those zeros and ones represent data. And we said that the data can represent instruction or data. So the instruction A, C equals A plus B literally is this. I'll rewrite it down. This is the most important part of today's lesson. C equals A plus B to a computer means this. C is actually an address in memory. C is an address in memory. A is also an address in memory. B is also an address in memory. It's an address in memory where things are stored. So for C, this is the address in memory to be stored. And A is an address in memory to be fetched. And B is an address in memory also to be fetched. So I want you to listen to this carefully. The CPU fetches the instruction C equals A plus B. That's step one. What is the instruction C equals to A plus B? It's literally a block of code that contains zeros and ones. A part of those zeros and ones represent the address of B, the address of A, and the operation of plus with the address of C. So all three pieces are there inside the block of zeros and ones. Does that make sense? So we fetch the sequence of zeros and ones. Part of the zeros and ones are the address for C. Another part is the address for A. Another part is the address of B. And another part is the operation code, the address of the operation, what job we're going to perform. So that's the first step. We fetched it. We've now put it inside where? A register inside the CPU. So that's the fetch operation. The next operation, decode, means we need to figure out what this instruction means. So since C, A, and B are all addresses, the decode function means the CPU will now read and interpret this as I need to fetch A, I need to fetch B, and when the computation is over, I need to store the results in C. So we will now, after fetching that instruction, the decoding means we will now go and fetch A and fetch B. What is the value at address A? What is the value at address B? In this, our example, A is 3, B is 2. So we'll go to memory and fetch 3 and fetch 2. How did 3 and 2 get into memory? 3 and 2 got into memory via an input-output device. Somebody typed it in. So on my computer, I said 3 plus 2. I hit enter. So I submitted that instruction. So when the instruction was fetched, it was a sequence of zeros and ones. The CPU fetched it, then it decoded it, and now it can begin working on it. We have the value of A, we have the value of B, and we have the operation addition. So what happens next? What happens next is execution. So in this example, the execution is handled by the arithmetic and logic unit. So this guy performs arithmetic, that's mathematics, and logical operations. That's what we did last week, logic operations. So it performs arithmetic and logic operation. Once the arithmetic and logic operations have been done, or the arithmetic operations have been done, a result is generated. What do? We then further go ahead and store the results inside the registers. And from the registers, we transmit it back to the RAM at address C in this example. And then from address C, it can be sent to an output device like a screen where we can now read the answer. Is this clear to everyone? Fetch, decode, execute, and store. Everything you fetch is a sequence of zeros and ones, which usually represents the address of where data can be found on memory. We then fetch whatever data we need, and then we perform the operations based on an operation code, and whatever results we generated, we store those results first in a register, and then from a register, we transmit it back to memory. And from memory, it can then be transmitted back to an output device, or it can be saved in the hard drive for use later, in case we just wanted to process and store. So that is how a CPU does what a CPU does. So the CU is responsible for movement of data and decoding of instructions. The ALU is responsible for, its name is arithmetic and logic unit. So what does it do? It performs calculations, and these calculations can be arithmetic or logical calculations. That's all it does. It performs calculations. Now, what about these registers? Let's spend a moment with these registers. We define these registers as electrical components or circuit components that store data for the CPU. It means whenever the CPU is operating on an instruction, the CPU only operates on one instruction at a time. Have you guys done any programming? Python? All right. So in Python, a line of code, at the end of the line of code, what do you put? A semicolon, correct? In Java, a semicolon. In Python is what? Nothing? You sure? All right, just checking. So every line of instruction you have, whether it's Python or Java, every line is considered one instruction. So when your CPU fetches code, it fetches one line only. And when it operates on code, it operates on just one line at a time. So your processor has something called the processor clock speed. The speed of a processor is how many instructions it can run through in a second. So if you look at a typical computer, it will be rated, a typical CPU, it will be rated in gigahertz. So for example, my computer is I believe a 3.4 gigahertz computer, and it has 10 processing cores. So that means it has 10 individual processors, each of which has a speed of at least 3.4 gigahertz. What does 3.4 gigahertz means? It means it can perform 3 billion. Gigahertz means billion. It can perform 3.4 billion instructions every 1 second. So it can fetch, decode, execute, and store 3 billion instructions approximately every 1 second. That's how fast these devices are. So many of your programs are made up of hundreds or thousands of lines of code. So those hundreds and thousands of lines of code can be fetched, decoded, executed, and stored in a fraction of a second. And imagine if I'm playing music. Playing music is the same as reading a book. You take it line by line, you read it, and then you interpret it. So the computer does the same thing. It fetches the first line, then it decodes it, and it sends it to the speaker. While the speaker is playing that first line, it fetches the second line, decodes it, and sends it. Fetch, decode, send. So it keeps building the song till it reads the entire data file. It's going to be performing the operation of translating or transcribing the data inside the file that makes up the music and converts the zeros and ones into vibrations in the speaker using a particular program. The compiler. Where is a compiler coming into this picture? Okay. So one of your classmates is asking, if I run code, the compiler, how does the compiler fit into this? You have to understand that the compiler is not part of your computer. The compiler is a tool that translates your high-level programming language into machine code, zeros and ones that your computer can run. So if I write a program in Java or in Python, my computer doesn't speak Python or Java. So this tool called the compiler will run it first and convert the program you wrote into something called a binary file. And inside that binary file is your zeros and ones that make up the instruction that represent the calculation you want to perform. So the compiler is not in this relationship. The compiler is just something that helps translate the code you've written to binary code. So when you want to run the program, the computer doesn't run your Java or Python, it runs the binary code that has been compiled. Any other questions? Everything good? People at home, can I get a thumbs up if everything is clear thus far? We've not talked about the cache controller yet. We've just talked about the main CPU. We'll get to the cache controller. So people in class. Mm-hmm. Mm.
We have the CPU like interface unit and the CPU and the ALU. So this picture is like, where's the interface unit?
Very good. So one of your classmates is asking about the interface. So let's talk a little bit about the interface. First of all, what is the definition of the term interface? An interface is best understood as a point of connection. For example, this tablet I have here is just a, what do they call it? They call it a pen display. It has a USB-C interface, which is what it uses to connect to my computer. My computer has a HDMI interface. So if I wanted to connect wired to my projector or my TV, I could use that interface. So an interface is a point of connection. There are two types of interfaces in a computer, namely a hardware interface and a software interface. Let's explain. Generally now, I first need you to understand, again, this is one of those terms that is ambiguous. It means many things. So the term interface is a point of connection. I said you have two types of interface, which can be hardware or software interface. Now, apart from the hardware and software interface, you also have something called a user interface. All of these things mean slightly different things, but they all represent a point of connection. So for example, you see the application I'm using here. This is called OneNote. This is the interface of OneNote. I can communicate with OneNote by clicking, dragging, and performing certain actions. The job of the interface is to translate my actions into instructions for the computer to perform. Does that make sense? If I have a calculator, so this is a virtual calculator on screen. This calculator has an interface. The buttons that I press, the 1, 2, 3, 4, all the way to 9, the plus, minus, whatever, also an interface. It's my point of connection with the device through which I communicate with the device. So the job of an interface is translator. Now, this is what a user interface is. In another term, an interface can be the physical connection, USB-C, HDMI, and so on. Physical interface, that's hardware interface. 3.5 millimeter headphone jack, so on and so forth. Wall socket plug, 3-pin, 2-pin, all interface. Connect things to. Then you have what we call the software interfaces. These are called ports. So software interfaces are also called ports. Are you guys doing introduction to networking now? So you know what ports are, right? Do you know what communication ports are? Huh? No, the Ethernet is also a hardware interface. The communication port in networking represents this. On a typical computer, you have one network interface card. But you have many applications that want to use that network connection. Think of it this way. If this classroom was a computer and all of you were applications running in that computer, and there's only one telephone on the wall for this entire classroom to share. So whoever wants to order pizza has to use this one telephone. The problem is if you use this one telephone and you order and they ask what's your address, you're going to give the address of this room. So when the delivery guy brings the pizza, how does he know who the pizza belongs to inside this room? Since everybody in this room has the same address. When an application tries to connect to the internet to get data and the data returns, how does the computer know who this data belongs to? Huh? The IP is the computer's address. Nope. The MAC address is also the computer's address. Huh? What is private address? No. Those are the same thing. It's still an IP address. The what? What do you mean Bluetooth? The ports for communication can be Bluetooth, it can be Ethernet, it can be anything. But the port that we're talking about now is referring to a number typically that represents the name or the association with the application. What that means is if I come to the telephone and I order pizza and I give this address, my IP address, I will add to my IP address my name. So that name is a port number. So every application that wants to connect to the internet, the computer's operating system will assign it a communication port number. So the computer's address, the computer itself, has an IP address. The connection inside here, this single connection is a port, and you can have multiple port numbers. Each one can be associated with a particular application. So this is called a communication port. It's a software description. So every app running will have its own individual communication port number. So if I go back to my activity monitor here, I can go under my network to see which of my applications is actually transmitting packets to the internet. And you can see here Microsoft Teams has transmitted about 900 megabytes worth of packets. So it will be associated with a specific port number. Is that clear? All right. So let's get back to business. So thus far, what have we looked at? We've looked at the basic components of the CPU. We're about to dive into the registers. After we dive into the registers, we can now come to the cache controllers. So in case you're starting to feel sleepy, now is a good time to wake up. We're about to talk about something very important. Registers. What is a register? It's a small storage device for storing data and instructions as they are being operated on inside the CPU. So if I fetch one instruction, all the components of that instruction will be stored inside registers. while my computer is decoding and executing them. When it finishes, we store the result, and then we fetch the next instruction, we save it, we decode it, we execute it, we store the results, and then we fetch the next instruction, and so on and so forth. So there are two types of registers. The first type of registers are called general purpose registers. So what are general purpose registers? General purpose registers are registers that can store any type of data. You remember when we talked about data, I said data is an ambiguous term that can mean data or instructions. So a general purpose data stores data or instructions, stores anything, stores a collection of zeros and ones that can represent anything. Then you have special purpose registers. A special purpose register is a register that is designed for a specific function. So let's go through them one by one. The first special purpose register is called the PC, otherwise known as the program counter. So what is the program counter? Okay, hold on. I'm just going to pause for a bit. All right, so as I was saying, so sorry for that interruption. As I was saying, there are two types of registers, the general purpose and the special purpose. So we begin with the program counter. Now, this is the most interesting bit. This this special purpose register called the program counter. Here's how it works. You remember what I said? When you have an instruction, you read it line by line. But when you're reading a book, when you've read one line, how do you remember where the next line is for you to continue your operation? In other words, if your book has 10 lines, you've read line 1, you need to go to line 2 next, then line 3, then line 4, and so on and so forth. So how do you know which line is the next line? So some people, when they read, you'll see they'll use their fingers to put on the line that they're reading so that when they finish, they don't skip a line. So that's exactly what the program counter does. The program counter stores the address of the next instruction to be run. So this program counter stores the address of the next instruction to be run. stores the address of the next instruction. Now, it's important for you to remember that we're talking of addresses. It stores the address of the next instruction. In other words, if I'm reading line 1, if I fetch line 1, the address is already pointing to line 2. And if I fetch line 2, the address is pointing to line 3, and so on and so forth. Very simple. Its job is to tell me who to fetch next. You remember CPU, fetch, decode, execute, store? The job of the program counter is to give me the address of which instruction to fetch next. Now, the second special purpose register is called the IR register. IR stands for instruction register. Instruction register. Now, like I said, data moves in and out of the CPU, controlled by the CU. Data can represent data or instructions. So when you're moving a piece of instruction or a piece of data into the CPU, if that data happens to be an instruction, it is then saved inside the instruction register. And if it's just regular data, it will be stored inside another general purpose register. It's important, it can get a bit confusing now. We say that the program counter and the instruction register are partners. Program counter points to the next instructions to be fetched. Instruction register is ready to receive that instruction and save it. So if I fetch something from memory and that something is an instruction, it will be kept inside the instruction register where it is then decoded. So what does the instruction register do? It holds instructions while they're being decoded. So when we say fetch decode, if we fetch an instruction, we put the instruction inside an instruction register, and then we go about decoding it. After decoding, we can then execute. The next register, the next special purpose register, is the memory address register. So MAD stands for memory address register. Memory address register. What does this guy do? It stores the address of what is to be fetched. And what is to be fetched can be data or an instruction. So it stores the address of what is to be fetched. Its partner is the memory data register, also called the buffer. Its job is simple. Its job is it stores what has been fetched. So what exactly are we talking about here? At this junction, it's important to remember that these registers are like tiny little gremlins inside the CPU helping to do things. So when we said the CU helps move data in and out of the computer, you want to think of the CU as the managing director of the company. And he has some secretaries, 2 secretaries, memory address and memory data. And the job of these secretaries is he tells them what to go fetch, they go fetch it and bring it. So these two, the memory address register and the memory data register, the address register shows the address of what we want to fetch. The data register stores the actual data that we have fetched. So think of them as 2 partners. One points the way, the other guy does the heavy lifting. One shows where, the other picks up and brings to the CPU. So the CPU gives them an address. It says, here's the address of what I want you to fetch next. Where does the CU get the address of what to fetch next from? From another circuitry called the program counter. So the program counter, the CPU says, I want to do fetch, decode, execute, store. What is the next thing I'm supposed to fetch? Secretary. So the program counter secretary gives him the address. This is the address of the next job. So he takes it and then gives it to another secretary called the memory address register. He says, here, memory address register, go fetch this for me. So the address register then goes and then it activates the location in memory where the address specifies. And then the data register goes and picks it up and copies it now from RAM into a register. But which register does it put it in? If what was fetched is an instruction, we put it in the instruction register. But if what we fetched is data, we put it in a general purpose register. That makes sense? So this is the relationship between the registers and the CPU. So the memory address register and the memory data register, partners responsible for moving data in and out of the computer. Also, if we finish calculating, let's say we fetch the instruction 3 plus 5. Here's what happens. Sorry, C is equal to A plus B. So C equal to A plus B is the instruction we fetched. Who fetches it? The address where that instruction is in RAM. C equals A plus B is actually in RAM. The CU gets an information of the address from the program counter of where that instruction is. So it then gives it to the memory address register, who then goes to memory and activates that cell. Then the memory data register picks up C is equal to A plus B. So when we bring it into the CU, we figure out that it's an instruction, C equals A plus B. So we then store it inside the instruction register. Then we decode it while it's on the instruction register. What does decoding mean? Decoding means we read it, it says C, which is an address, is equals to A, which is also an address, plus B. So now we need to go fetch A and B. And who fetches A and B? The memory address register and the memory data register again. So when we fetch those, when those data of A and B come in, where do we store them? Inside a general purpose register. So now we fetch the instruction and we've decoded it. We have all the data elements we need. If that example is confusing, think of it this way. You are the computer. You're in your kitchen and you're about to cook and you're following a cooking recipe. And the first part of the cooking recipe is what? List of ingredients that you need to go fetch. So you need to go get it. When you get it, you need to bring it somewhere and you need to store it. Once you have all your ingredients, then you can begin your baking or your cooking process. So the same thing, when an instruction has been fetched, all the data and all the resources that we need to execute that instruction has to be aligned and arranged. Then only we can execute. So that decode process is the process of figuring out what the instruction is and getting all the associated data elements so that we can go ahead and perform the action. Last register is called the status register. Now, in this status register, it stores the context of what is happening. So it stores the context of operation or of current operation. In other words, what is the computer doing right now? Am I running Microsoft Teams? Am I performing a calculation? Which program am I running? Which book am I reading? What is actually going on right now? So in this classroom, you are aware of what's going on. We started this lesson and we've been moving into subject discussion to subject discussion. You are cognizant. You know what we're discussing. You know exactly where we are. That is your status register. Without a status register, you have no idea what's happening and what you're doing. So the status register stores information about what is actually currently going on in the computer. Does that make sense? All right. The last thing we're going to be talking about now is these lines, the interfaces and the buses now. So in this CPU here, I want you to notice, I'm going to color some green dotted lines. You see here between the hard drive and the RAM, you have this wire that is connecting these two. Those green dots are interfaces. They're literally sockets. A cable fits into that socket. So these red lines are buses. What is a bus? It's just a cable that consists of conducting wires that can carry electrical signals from one device to another. They're nothing special. It's just conducting cable. It's just a wire. Here, between the RAM and the CPU, also an interface. Between the RAM and the input-output device, also an interface. Have a question? One coming out, the other going into the other side. So again, if you look at my device here, I have USB-C here, USB-C here, cable. This cable is the bus. It enters here, it enters it. So where it enters is the interface. So the interface is also called a module. What's a module in technology? A module, like this course is called a module, right? It means a distinct component that fits into another. So this module, its job is to translate whatever this device says to be transported onto this wire. And this input interface here is a translator for this device to condition the signal into a language that it understands. So this guy might be operating at 5-6 volts. This guy might be operating at 19 volts. They can't talk. They speak the same electricity, but not the same voltage of electricity. So conditioning and formatting has to happen for transmission of data signals. Just like when I think, it is not what I think that I transmit to you. It has to go through my mouth and I convert it into a sentence. And then it's not my sentence that goes into your head. It's your ear that picks up the sentence and then reinterprets it into meaning and feeds it to your brain. Interface to interface. So that's what's going on. Does that make sense? So what is a bus? It's just a cable that connects two or more devices together via an interface. So there are two types of buses. There is point-to-point and there is multi-point. What is point-to-point? A bus that connects two devices uniquely, like this one, point-to-point. I cannot connect another device with this connection. It's one-to-one, point-to-point. I can have another type of bus that it goes into one, but it has two mouths. It comes out and it joins two other devices. So multi-point. All right. Here's a something like that. So here, if you look at the CPU, you see the CPU has a multi-point connection with the RAM and the input-output devices and the hard drive. Let me show you what it actually looks like in real terms. So I'll just scroll in here. I want you to take a look at this image here. Uh-oh. So let me zoom in. You see, here's the CPU, here's the memory, here's the GPU, and here's the hard drive. They're all sharing one bus. So when I drew it in my diagram, you saw the individual wires. That's not really how they are. How they are is that there's a single bus that connects these four devices together: the hard drive, the memory, the CPU, and the graphics adapter. So it's a multi-point bus. But inside the CPU, between the CPU, the CU, and the LU, they have a point-to-point bus. So that's an example. So point-to-point simply means one-to-one, and multi-point means more than one. There is also the nature or the direction of transmission of these buses. Some buses transmit data just one direction. We call those simplex buses. Another can transmit both direction, but only one at a time. So it means it's either sending or it's either receiving. So we call that half duplex. Then there's another bus that can send and receive at the same time. We call that full duplex. And there are many devices. You see, your USB is a universal serial bus. The bus is the wire, And the bus can carry 4 types of signals. What are the signals that a bus can carry? They are as follows. A bus can carry, hold on. Let me escape the presentation. Right. A bus can carry 4 types of signals. One, it can carry power signals. That is why you're able to charge your phones through USB. The USB serial bus also has a power line. If it didn't have a power line, you won't be able to transmit power. 2, it can transmit addresses. That is why you can connect a USB hard drive. A hard drive is an addressing device. You want to read, you have to give an address which to read from. You want to write, you have to give an address which to write from. So the bus, the cable connecting the hard drive to the computer, has to be able to carry addresses so that I can know where to read and write from. Thirdly, data. Have you ever connected 2 devices with the cable and doesn't work quite well? I remember when I first got my Nintendo, I think it was my Wii U. It needed a special data cable. If you use a regular HDMI cable, it doesn't carry the signal. I think that's also true for the PlayStation. If you use a simple, flimsy HDMI cable, it's not going to carry the signal. In fact, you see this USB cable that I'm using here? This guy is made by Basus. It's a very expensive cable, and it needs to be high quality because it's carrying video signals. If you used another typical USB-C cable, image will not appear here. It will carry data. It will act like a gigantic trackpad, but I won't get the image. So the cables, the buses, the quality of the buses determines how much data you can actually transmit over the line. And the interfaces also determines what you can transmit. So USB 1, USB 2, USB 3, and USB 4 are all different standards that can carry different amounts of data signals. And if you want to see that detail, you can go on to Wikipedia. Let me just show you the quick note. If you go to your internet and just do USB Wiki, in the Wikipedia article, you'll see a description of all the standards, as you can see them here. So you have the connection type, and you have the standard USB 1 all the way to the current USB 4. And you can see the amount of data each one can carry. Your USB 1 is low speed. It can transmit at 1 megabyte per second. USB 2, 480 megabytes per second. This is your Apple, the poor man's iPhone. The regular iPhone, right? The regular iPhones have USB-C type 2. The expensive one is USB type 3, which can do up to 5 gigabytes all the way to 10 gigabytes. USB 4, which is called Thunderbolt, which is only existing, I don't think any of the iPhones have it, only the Macs and many PCs have it, is 80 gigabytes. So in other words, this cable is capable of 80 gigabytes per second. That's why it can carry image signals. But this cable, what is it carrying right now? This guy doesn't have a battery. My tablet here doesn't have a battery. So the power, the addressing, as well as the image signals, and well as the input signals, two-way. So it is a bus that is full duplex because it's input and output, and it's type 4 because it's carrying a lot of data. And this cable needs to be thick and well made in order to be able to tolerate all of that. So power, address, data, and lastly, control signals. So what's a control signal? I can press a button, a shortcut key on my tablet to get it to do, undo, on, off. Just like if you have a printer connected to your computer, you can instruct the computer from the printer by hitting print. It will transmit to the computer and the computer will start scanning or whatever. So you can have a bus that transmits a control signal, on, off, start, stop, read, write, whatever. So data, address, power, and control. And we said a bus can be classified into three ways: how it connects, point to point or multi-point; how it transmits, serial or parallel. Serial means data bit by data bit. Parallel means multiple lines connected to the bus. So for example, inside this cable, there are multiple wires. It's not just one big wire. There are multiple wires. One is for power, one is for address, one is for data, and so on and so forth. So a parallel bus is a bus that consists of multiple lines that transmits data at the same time. Whereas a serial bus is one single wire that transmits bit by bit. And then you have mode of connection, or rather direction of transmission, which is simplex, one direction, half duplex, one at a time in both direction, or full duplex, both at the same time. Let's finish. So we've looked at the CPU, and we've looked at the memory, and we've looked at the general relationship between the CPU and memory. So what have we learned? We have learned that all the components of a computer are directly connected to the CPU via cables called buses. The CPU performs four fundamental functions: fetch, decode, execute, and store. The fetch and the decode is handled by the CU, the control unit. The control unit controls all the components inside the CPU. The CPU controls all the components inside the computer. To execute, the ALU is responsible for execution, and for storing of results and storing of fetch data, the registers are responsible. We then said the registers are of two varieties: special purpose and general purpose. Of the special purpose, we have 5 types: program counter, instruction register, memory address register, memory data register, and lastly, the status register. We then said all of these bad boys are connected via a bus, and that bus has characteristics. First, what kind of signals can it carry? Power, data, address, control. How can it be connected to a device? Point to point or multi-point? What mode does it transmit? Serial or parallel? And what direction does it transmit? Simplex, half duplex, and full duplex. The last thing left now is this cache controller. What is a cache and what is a cache controller? Now, the cache is a special type of storage that is also in the CPU. So a computer literally has 4 layers of storage: hard drive, RAM, cache, register. Let me write it down so that it's clear. You have your hard disk, and then you have your RAM. All of this store data, and then you have your cache, and then you have your registers. Now, if you have a storage device, what is the best advantage your storage device can give you? 2 things. You want your storage device to be as big as possible so that you can store more data. And you want your storage device to be as fast as possible so that you can read data quickly and you can write data also quickly. So read and write speed and capacity. But there's a big problem. The faster a device is, the more expensive it is, and the more components it needs. The more components it has, the bigger physically it is. So if you want to get the fastest device, it will be super expensive and it will be gigantic. A gigantic component means it will consume more battery power and it will consume more physical space. So because in a computer, we want both the speed and the capacity, so what we do is we get the best of both worlds in 4 divisions. We have the hard drive, which is biggest in capacity, but is the slowest. We have the RAM, which is faster than the hard drive, but not as big. Then we have the cache, which is much faster than the RAM, but not as big. And then you have the register, which is teeny tiny, but crazy fast. You might start to think to yourself, how does that make the overall thing faster? It's very simple. Think about your kitchen. In your kitchen, you have your kitchen cabinet. You have your kitchen drawers. When you're cooking, the quickest place to get things from is from that drawer. It's right here. You just go down and you pick it up. This is your register. Your cache is your store. You know, in the kitchen, you have a little storage room. That's your cache. Or rather, let me do it this way. You are the CPU. In your kitchen, when you pick up something to use, you're picking it in your hands. So your hands are your registers. They're the closest things to you. If something is already in your hand, that's the quickest you can pick it up. Your drawer, your cache. The most important things, but it's small. Then your kitchen store, your RAM. It's bigger, but it takes you about a minute to get in and pick something. Whereas this guy, just a few seconds. And this guy, if something is already in your hand, it's already in your hand. If the ingredient you're looking for is not available in your hands, it's not in your drawer, and it's not in your store, where do you have to go to? Supermarket, which might be a 1-hour drive. That's your hard drive. And I'm not exaggerating. That's how the difference in speed is. It's so much faster to retrieve something from your registers, and it's slightly slower to retrieve it from your cache, and it's slightly slower to retrieve from your RAM, and it's much slower to retrieve it from your hard drive. So this is why you have these 4 layers. Just like in your kitchen, you can't buy the entire supermarket and put it inside your storage room. It's too expensive. You don't have enough space. But you have a storeroom still, no matter how small it is. It's useful. It provides longevity and so on. So this is the same concept that the, that the computer engineers actually use to design these computers. So I believe that's that. The last thing on the slides here are the instruction formats, which we've already looked at. I've told you an instruction is just a sequence of zeros and ones. And the zeros and ones contain 2 types of data: operation code and operand address. So the addresses and what operations to perform. So you can see here, you can see here, you have the operation code and the address field. So the address for A, B, C, this is for a 32-bit computer. A 64-bit computer, each block will be 64 bits wide. And I think that's that. Let's check if there's any other missing piece. So these are just some examples of different instruction formats, which are not too important. And these are examples of some register functions, which you can read from the textbook. It's not complicated. We've brushed a few, we've brushed a little bit on top. So now in preparation for your test, you have everything up until what we've actually covered today. But the main focus of the test is logic gates. So what I've done is on your Moodle page, let me see if I can find it. If you go to your Moodle page right now, I think you will find go to your Moodle page. I can't seem to access it right now. On your Moodle page, you will see a practice test. From the practice test, you need to download the lockdown browser, and you can then view it from there. So in the next time we meet, it will be D-Day.